All right, welcome back, everyone. We're going to do a few more examples for this limit definition of derivative, just for the practice. It's good to practice these things. So let's try example 3. And we're going to calculate, given this function square root x, we're going to calculate the limit definition of its derivative. So first thing, we see this phrasing here, limit definition of derivative. What does that mean? Let's write down the definition. So f prime of x is equal to the limit, as h goes to 0, of f of x plus h minus f of x all over h. There's our limit definition of derivative. Okay. So now let's actually work with this f of x plus h term. So we're going to plug x plus h into our function, into our original function here. So let's just look. Wherever we see an x here in this equation, just change it to an x plus h. Change this one, we get f of x plus h. Change this one, we get square root x plus h. There we go. So let's fill that in. Can't write in a highlighter. Here we go. Square root x plus h minus square root x. So that's square root x plus h. That's what we get when we plug x plus h into the square root function. And then f of x, that's just the original function. So just square root x. And this is all over h. All right. So we want to calculate this limit. And for all of these limit definition for all of these problems involving the limit definition of derivative, they're all 0 over 0 indeterminate forms. Because, well, you can try. Plug h equals 0 into this. You get 0 on the top, you get 0 on the bottom. So we have to use more of our advanced algebraic techniques to kind of help us work with these limits. And so we've seen ones like this before involving square root functions. And our trick, that's really what it is to rationalize the numerator. And we do that by multiplying by the conjugate. All right, so what are we going to do? See what we have in the top here. We have square root x plus h minus square root x. We're just going to multiply by a fancy 1. So we're going to multiply this whole thing by its conjugate. So its conjugate is the exact same expression. Only difference is we're switching it to a plus. So it originally was a minus, we've switched it to a plus. So that's the conjugate. Now if we take something and we multiply the numerator of a fraction by something additional, it's changing the fraction. So we don't want to really change the fraction here. We got to keep things balanced. So if we do something to the numerator, we got to do the exact same thing to the denominator. That's what we're going to do. We want to throw this in here. We have to multiply our denominator by this as well. Okay, so we're getting there. Now let's actually do the multiplication. So let's take this numerator, multiply with this numerator. And this is where the fun happens, is because we get a lot of canceling. So we take this square root x plus h, multiply it with this square root x plus h, and what do we get? Well, we just get a nice x plus h. Then we take this negative square root x, multiply it with this positive square root x, and what do we get? We get a minus x. Okay. And then if we took this positive square root here and multiplied it with this positive square root x here, and then took this minus square root x and multiplied it with this positive square root x plus h, all of that would cancel because we have a positive version of those two terms and then a negative version of those two terms multiplied together. So the positive and negative versions would just end up canceling out. So when we multiply this whole thing out, we're using FOIL there, we end up with x plus h minus x. So there's a little bit of work there for the numerator. Let's be lazy about the denominator though. So we'll just write it as h times, let's not even do any multiplication. We're not going to distribute that or anything. We're going to leave that alone. Actually, it's easier if we do it that way too. All right, so got a little more canceling here. The x's cancel. That's nice. So x minus x. And we're left with just an h. Okay. And we have h over h. And we're seeing we're going to have more canceling times those square root terms. Let's cancel those h's, which is nice. And as soon as we cancel those h's, that's what was really giving us that indeterminate 0 over 0 form. So as soon as we do that canceling, we should try evaluating then. So that's what we're going to do next. So we have 1 over the square root of x plus h plus the square root of x. And now we're just going to plug in. And the reason why we can do that, so we're going to evaluate at h equals 0. So we can't just always do that. But in this case we can. And the reason is because this is a continuous function in terms of h. So square root function is continuous. If we add something to add square root x, that's continuous. So when we add two functions together, we get a continuous result. And if we divide, division also maintains continuity as long as we're not dividing by 0. And we're not here. So h is approaching 0. And what we end up with when we plug that in is 1 over square root of x plus 0 plus square root x, which ends up being just 1 over square root x plus square root x. I mean, that's okay, but we could do a little better than that. We have 2 copies of square root x, so we can add them together and get 1 over 2 times the square root of x. That looks a little nicer. So we're just adding the coefficients there. 1 times square root x plus 1 times square root x. That's a little nicer. All right, so there we go. We got our derivative using this rationalization technique. All right, let's try another one, just for the practice. Example 4. We want to find the derivative of this rational function. So this is a rational function we're going to do. Polynomial divided by a polynomial. This one's going to be a little, nope, rational function. Started writing what I was saying. It's a polynomial divided by a polynomial. All right, and we're going to do the limit definition of derivative here. So as soon as we see that, there we go, phrasing, we write down the definition of derivative. F prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Okay, we got our definition down. Let's start with this f of x plus h. So we go to our function. We're going to plug x plus h in wherever we see an x. So I'm going to change this x to an x plus h. I'm going to change this x to an x plus h. And then we got one more, right? Yeah, x plus h right there too. So let's do that. So we're going to end up with, for this f of x plus h, what are we going to end up with? We're going to end up with 1 minus, and I'm putting parentheses here. So it's actually good practice. Whenever we replace an x, probably with an x plus h, actually replace it with a parentheses x plus h. So we don't forget about the negative here. We're going to have to distribute that over the parentheses, so to the x and to the h. Just a little caution there. And then 2 plus parentheses x plus h. So that's just this fraction f of x plus h. And I did it. I put the limit sign up too high because this thing's going to be, it's going to be fractions on top of fractions here. But let's see. Let's throw in our original function as well. So we're going to have subtraction and then just our original function. So 1 minus x over 2 plus x. And then this is all going to be over h. And yeah, let me rewrite that. Kind of center it on the fraction sign there. And this is looking a little confusing, my opinion. Whenever we have fractions on top of fractions, my eyes, it gets hard to read. So I like to rewrite this with just a little property here. Instead of having a big fraction, so instead of having this whole thing, which we'll call A, divided by something which we'll call B, instead of having A over B, we can, instead of dividing by B, we can multiply by its reciprocal. So we can take the reciprocal 1 over B and multiply that into A. So the benefit of doing this is it just kind of splits up all the fraction signs, just so things aren't, so confusing. It's easier to make mistakes. In my opinion, it's easier to make mistakes with this. So we're going to write this as the limit as h goes to 0. Instead of dividing by h, we're going to put a little 1 over h in front, multiply by its reciprocal, and then we're going to take all of this that's in the numerator and we'll throw it into some brackets right next door. And we'll clean it up as we go. So let's distribute this negative. So we get 1 minus x minus h all over 2 plus x plus h. And then we're subtracting, and we have our other fraction. There we go. A little bit easier to read. And there. A little bit easier to read. All right, so now we need to work with this term that's in the brackets. And we know with these limit definition, this is a 0 over 0 form. So with 0 over 0 form, the idea is we need to work with this complicated piece until eventually we get something where we can actually cancel off this 1 over h. This 1 over h is what's kind of giving us, or at least contributing to, the indeterminate form. So as soon as we get this canceled off, we'll be in good shape. So we need to work with this term inside the brackets. All right, so whenever we have different fractions like this, the idea is we want to actually do the subtraction, or if there's addition, do the addition there. But we have different denominators. So we've seen things like this before. We need to get a common denominator. All right, so what's our common denominator going to be? Well, the easiest way to get that is just to take this one and multiply the two of them together. All right, so what are we going to get? We're going to have the limit as h goes to 0. We have that little 1 over h in front still. Now we're going to multiply our two denominators together. So we're going to have the 2 plus x plus h from this first fraction, and we're just going to multiply in this other denominator, so we'll have a 2 plus x. Now, what was originally there for the numerator? In the first fraction, it was a 1 minus x minus h, so that's still going to be there. And then we had to throw in this 2 plus x. That wasn't there originally, so we can't just do it to the denominator. We have to do it to the numerator as well. We got to keep things balanced. So a 2 plus x is going to go up there as well. Then we subtract. And we want to do the same thing, get a common denominator for the second fraction. So let's start by writing out what that second fraction originally was. 1 minus x over 2 plus x. Now to get a common denominator, we have to multiply by this 2 plus x plus h term. So let's throw that into the denominator. We can't just throw it into the denominator. We also have to throw it into the numerator as well. So a 2 plus x plus h is going to go up there as well. All right. All right, we're getting there. It's looking more complicated as we go, but there's going to be some fun canceling coming up. But before we get there, we got to do some multiplication. We got to multiply all these out. So let's multiply out these two, this numerator here. What are we going to get? And, there's different ways to do this. The way I like to do it is I find the smaller piece, the 2 plus x here in this case, and just go with each term there. So I'm going to start with the 2, and I'm just going to distribute that in. So I'm going to distribute it to the h, the x, and then to that 1. When I do that, I get a 2 minus 2x minus 2h. So I've distributed in the 2. Now let's go to the plus x. So I'll just distribute that in to this first piece. So I'm going to distribute it to that negative h, the negative x, and then that positive 1. So when I do that, I get a plus x minus x squared minus xh. And then a nice set of parentheses there around everything. All right. So that's us multiplying all this out. And we're going to combine this into one fraction. So we're going to have a big subtraction sign, because that's what originally was there, subtraction. And we'll have a big fraction now. And then in the denominator, what's our denominator going to be? It's going to be this common denominator. And let's be lazy with this. So let's not multiply this out. And this is actually going to be helpful. Yeah, not too helpful, but it's okay if you multiply it out. But it's actually easier if you don't in this case. But we do have to multiply out this numerator. So a lot of times when we work with fractions, a lot of the work gets done with the numerator. Denominator, not always, but a lot of times not too much happens there. And that's the case here. We're not going to do anything with this denominator, but we got to multiply this out. So again, start with the term that has the fewer pieces in it, so this one, and then just kind of distribute it all the way through. So I'm going to distribute this 1 to everything over here. When I do that, again, let's get a nice set of parentheses here. I get a 2 plus x plus h when I multiply everything by that 1. Then I'm going to take this negative x and multiply that right on through. And when I do that, I get a minus 2x minus x squared and minus xh. All right. So now kind of comes the fun part. We get to do all kind of canceling. So whenever we have a big set of parentheses minus a whole nother big set of parentheses, the way to kind of start is just to go term by term and kind of look for a similar term on the other side. So I'm going to start with this 2. And I want to look over on the other side. And right away, I see a 2 right there. So we have a 2. We're subtracting. And then I have another 2 over here. The 2's cancel. Then I just kind of go down the line. So I have a negative 2x. Over here, I want to look for a negative 2x. Got one right here. Those cancel. Then I have a negative 2h, and I don't have a negative 2h. I have an h here, so those do combine. Well, let's just hold on to that for now. So it's not a perfect cancellation. But here I have a plus x. Look over here, and there we go. An x right there, and we're subtracting, so x minus x, those cancel. Then I have a negative x squared. I'm subtracting, and then I look, I have a negative x squared here, so those cancel. Gone. And then I have a negative xh. I'm subtracting, and right there at the end, negative xh. Those cancel. So everything that's left, forgot my 1, so those cancel. And everything that's left, I have a negative 2h right here, and I have this h right here, and I'm subtracting. So all we end up with is a negative 3h in the numerator once we simplify this down. So I have a negative 2h minus a positive h. That gives me negative 3h. So let's write this out. Doing the limit as h goes to 0, 1 over h. And then the term in the brackets simplifies down quite nicely into negative 3h. Times 2 plus x plus h minus 2, or times 2 plus x. Make sure I got that right. 2 plus x plus h, 2 plus x. Yeah, there we go. All right. And we're in good shape here. So this is simplified down quite a bit. A little bit more we can do. So in here we have an h on the top. Down here we have an h, so those h's cancel. And as soon as we do that canceling, that 1 over h in front, that's normally giving us or contributing to the indeterminate form that kind of makes this a little bit more involved. So as soon as we cancel out that h in front, that's a sign that we're ready to do our evaluate the limit. So what we're going to do is we're going to plug in h equals 0 into this expression, and we get -3 over 2 plus x plus 0 times 2 plus x. And why can we do that? Again, this is a rational function. It's a polynomial divided by a polynomial, and we're viewing this denominator as a polynomial in terms of h. So h is the thing that's changing. So when we actually plug in, notice that I still have x's here. I'm not plugging in 0 in for x. I'm only plugging in 0 in for h because h is the thing that's going to 0. So our justification here, we're using direct evaluation, really continuity, because really this function here, this is a rational function in terms of h. So we can just plug right in. So we can evaluate that limit because it's a rational function and because we do not have division by 0 for that particular h value. Okay, let's clean this up a little bit. We end up with -3 over 2 plus x times 2 plus x. And that's fine, but we can do a little better than that. We have a 2 plus x times a 2 plus x, so those just end up being a 2 plus x squared. So -3 over 2 plus x squared. And that's our derivative, f prime of x. We worked hard for that one. That one took a little bit, but we got it. We got it. So notice when we're doing these, when we go through this differentiation process, we start with a function f in terms of x. We go through all this work, different based on different functions. But the end result is a brand new function f prime that's still a function in terms of x. All right. So we'll be working with these limit definitions of derivative a little bit more, kind of seeing some more applications, that sort of thing. But this kind of gives us a good starting point on different types of functions we should be able to do. So we've looked at being able to differentiate a rational function using the limit definition, square root functions, and then last time we looked at polynomials of degree 2 and 3. So those are some of the types of functions we should be able to do using this limit definition of derivative. All right. Let's stop there. So we'll see some more applications of this differentiation process coming up. But it's fun. These are always fun. I really like this one. You get a lot of canceling. It's always fun to do. Anyways. All right. So we'll see you next time. All right. Bye-bye.